Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture, if you recall, we talked about the shear stress calculation or the expression for the shear stress we have derived. Okay, when your bending moment is not constant, that is not the pure bending situation, when bending moment is varying. So, therefore, your shear force does exist, and based on that you have got the shear stress on the cross section, right. Okay. Now, as you know that most of the times you will be getting the rectangular cross section of the beam, okay, that is more common. So, let us see how we can extend the same knowledge, okay, same thing whatever we have learned to find out the shear stress, how it can be obtained for the rectangular cross section, okay, or the square cross section or whatever, I mean you generally get in the common practice. Okay. So, now already we know from our equilibrium condition that del sigma x, if you recall, okay, del x plus del tau xy del y equal to 0 and del tau xy del y del x plus del sigma y del y equal to 0. So, that you know from your equilibrium equation, right. So, now if the shear force does not vary, okay, if the shear force does not vary with x as we have discussed in the last lecture, the shear force, because there is no transverse load, the shear force is not varying with x, only the bending moment is varying. Since bending moment is varying, therefore, shear force exists, but they are not varying with x. Then if shear force does not vary with x, then the shear stress will be also independent of x, agreed or not. If there is no variation of the shear force, then how the shear stress will be varying with x. So, shear stress will be always also independent with respect to x. So, then in the second equation, okay, this part is 0, because there is, I mean shear stress is not having any variation with x. So, the first term of the second equation is simply 0, and we know from our previous discussion that in case of this type of problem, this class of problem like bending and this shear force, your sigma y is also 0. So, by default this equation, that is the second equation, is automatically getting satisfied. Okay. So, we need not to think about that. Now, we will be only dealing with the first equation, okay, which is more meaningful for us. So, from the first equation, okay, we can write simply del tau xy del y is equal to del sigma x del x. It can be written as del x minus mby by izz, that is the expression for sigma x, which is nothing but vi zz y, right, v, because del mb del x is nothing but v, that is the variation of bending moment with respect to x, that is nothing but your shear force v. So, vy by izz, right, v means minus v. So, minus minus will be becoming plus. So, from this I can simply write. So, therefore, if you come back to this figure actually, so we are considering the rectangular cross section as we have decided, and this is the and you know that the neutral surface or the neutral axis will be passing through the centroid of the cross section. So, it will be passing through the center of the beam, okay. So, this is h by 2, this is h by 2, okay. And on this plane, if we consider one element, sigma x is acting, okay, due to bending, you know, and now your because of your shear force your tau xy is also acting, okay, fine. And the bending moment on this section say MB and width of the beam is say B, and we are considering one section at say y1, okay. So, we will be finding out the variation of shear stress, okay, the magnitude of the shear stress from y1 to the top surface. I mean at say at y1 what is the magnitude of my shear stress. So, that we are going to find out, okay, fine. So, from the basic principle or from the fundamental principle we are trying to obtain that thing, and later on you can use that whatever you have learned right now, the tau xy equal to V, I mean in the previous class you have seen that tau xy is equal to Vq by Bizz. From there also directly you can get it, but we are coming from the basic principle, okay, fine. So, from this I can write, because we are interested to find out the shear stress or the variation of shear stress, okay, from y1 to the top surface. So, y1 to we will integrate that, top surface is h by 2, okay. If you look at this figure you will get it. So, del tau xy del y dy is equal to Bizz y1 to h by 2 y dy. I can write that, there is no issue, okay. Now, from this I can get minus tau xy, okay, y1 to h by 2 is equal to Bizz y square h by 2 y1, okay. So, which can be further written as, now your, because here actually we know, because tau xy is 0 at y equal to h by 2, already we have seen that the variation of your shear stress will be maximum at the neutral surface and it will be 0, simply 0 at the top surface, right, top and bottom surface, okay. So, when y is becoming equal to h by 2, that means you are reaching to the top surface. So, there actually your tau xy must be 0. So, that is at the top surface of the beam, right. Y is equal to h by 2 is nothing but the top surface of the beam. So, if that is so, then we can write tau xy, okay, at say y1, tau xy at y1 whatever is our objective is equal to V by twice Izz, okay, into h by 2 whole square minus y1 square. So, equation 8. So, you can verify that if you put y1 equal to h by 2, if you put y1 equal to h by 2, that means you are going to the top surface of the beam. So, if you are going to the top surface of the beam, this equation will give you tau xy is simply equal to 0. So, that is satisfying the condition. Now, if you put y1 equal to 0, if you put y1 equal to 0, that means you are at the neutral surface and then you will be getting the maximum value of your shear stress tau xy, and that is nothing but V by 2 Izz into h by 2 whole square. Agreed? Now, this thing we have got from the basic principle, right, starting from the equilibrium equation, and we have got it. The same thing you will be getting, okay, that you can do, you can try by yourself. So, same thing you will get if you consider the equation whatever we have derived in the last lecture, that is tau xy is equal to tau xy is equal to Vq by B I Z Z, where B is the width of the beam. So, there basically this is your say cross section of the beam, okay, rectangular. This is the center, okay, I mean neutral axis, okay, I mean neutral surface rather, normal to the board is your neutral surface. And if you want to find out the shear stress at some distance y1 from the neutral surface, so then basically your Q will be the first moment of this shaded area, right. First moment of this shaded area will be your Q, agreed, and this is your say h by 2, and this is also your h by 2, and this is your B. Okay. So, in the same process you can try, you can give a try. So, this V by IZZ will not be varying, I mean that will remain same. If you try to find out Q, that means the first moment of the shaded area if you try to find out, and then if you put in this equation you will be getting the same expression whatever you are getting here, okay. But that we, because this thing you can do at any time, because already we have derived this equation and you can use this equation to find out that. But what I wanted to show you that from the basic principle also we can arrive this thing at least for the rectangular beam, okay. So, now if you look at the variation of your shear stress for the rectangular beam as I told you, so this is the variation, okay. So, this is the variation of your shear stress, 0 at the top and bottom surface and maximum at the neutral surface, okay. Now, both equations whatever you have got, say d phi, do you recall that d phi ds is equal to 1 by rho is equal to mb ei zz, okay. So, equation say 9a, and you have got sigma x equal to minus mby by izz, so equation 9b, okay. Both these equations are in error, okay. When the shear force varies, and which is pretty common actually, right, along the beam. Now, I mean what we considered, we started with when we derived these equations we considered pure bending situation, that means shear force was not there. Then we have assumed that even if you have the shear force and if the shear force is not varying along with the x, okay, if shear force is constant, okay, with respect to x, then but your bending moment is varying with x, but in that situation also these equations hold good actually. But both these equations truly frankly speaking are in error when the shear force varies, and that is very pretty common actually. You may have different transverse loading condition along the x direction, that means along the length of the beam, along the span of the beam you may have the variation of shear force, that is pretty common actually. So, if that situation arises, okay, then these equations are in error, okay, along the beam, but the magnitude of error is small for long, slender beam, and consequently Qyx is equal to Vq by Izz, that means shear flow represents a good estimate even in the presence of a varying shear force. Okay? So, what I said, the most general thing is that your bending moment is also varying, shear force is also varying along the length of the along the span of the beam. If that situation arises, which is pretty common, then these both the equations are in error when the shear force varies along the beam, but the magnitude of error is pretty small for long slender beam, whatever we generally consider in the in our different structures or different kind of say civil engineering structures or any kind of say structure. If we use this beam, long slender beam, for those beams, actually these equations, I mean whatever error will be developed or generated by these equations, that will be pretty small. Okay. And consequently, the QYX, that is the shear flow, whatever we are calculating based on that, represents a good estimate even in the presence of varying shear force. Okay. Even because this equation was derived considering that your shear force is not varying with x, shear force was constant, but even if the shear force is varying with x, but still this equation estimates, I mean it gives good estimation of the shear flow. Now, what I mean to say that if you consider the very general situation, that means shear force and bending moment both are varying with x, still we can use these equations to find out the bending stress and the shear stress. Okay? That will not create much or significant error in the analysis. Fine? Okay. So, now thus at each section actually, thus at each section, okay, of a beam in the engineering theory of elasticity, elastic beam, okay, engineering theory of elastic beam, we take the bending stresses to be distributed according to (9b). Just now I have shown you, okay, equation 9b, and the transverse shear stresses to be distributed according to equation 5, okay, whatever we have seen earlier, independently of how your MB and your V shear force vary along the length of the beam. Okay. So, thus at each section of a beam in the engineering theory of elastic beam. So, now this is not the, I mean I should not say this is the actual theory or the correct theory, but this is the engineering theory and we are doing the engineering approximation to find out the bending stress and shear stress. So, we take the bending stresses to be distributed according to 9b, that means sigma x equal to minus mby by izz. So, that equation holds good, and the transverse shear stresses to be distributed according to equation 5, that is tau xy is equal to vq by bizz, independently of how mb and v vary along the length of the beam. Whether mb varies along the length of the beam or whether v varies along the length of the beam. So, that is quite immaterial, okay, for the time being, because we are talking about on the elastic theory of the engineering theory of the beam. So, we are doing little bit of approximation, but that approximation holds good, I mean that will not create significant difference in the result. Okay. Well, so in the next, I mean sometimes you will see in your different structural component, you generally use, instead of using say your rectangular beam, okay, you sometimes use T beam or I beam, you might have seen that. Okay. It is particularly very much say valid for your steel structure design, like this kind of beam you might have used, I mean you might have seen, okay, I beam or T beam. Okay. This is your I beam, this is your say T beam. You might have seen this kind of beam, okay, pretty commonly in your steel structure design or something like that. So, this kind of beam actually if you try to analyze and if you try to find out the shear stress distribution on this beam, okay, how they will look like, okay, or I mean what will be the variation and what kind of shear stress will be predominant in this particular type of section. It is not the rectangular section, right, rather it is having, so this is known as web and this is known as flange, right, these are the technical names. So, if you come across this kind of I beam or T beam, okay, then how your shear stress distribution will be varying, okay, or how, I mean which type of shear stress will be predominant. So, that thing we will be addressing in the next class. Okay. So, I will stop here today. In the next class we will continue with this kind of beam and we will try to conclude this chapter and then we will take couple of numerical problems. Thank you very much.